Centuries before the telescope, master engineers mapped the entire night sky with nothing but their eyes. These forgotten architects of the cosmos created celestial maps so precise they guided empires across oceans, and their story holds a crucial lesson for our digital age. By the end of this journey, you will understand how their ancient ingenuity secretly built the foundation for modern astronomy. We will uncover how they built computers from brass without electricity, and why their star charts are still correcting Earth's wobble today. What does it truly mean to see the universe not with a lens, but with patience? The night sky was their unchanging map, their calendar, and their sacred text. To label the centuries before the telescope as a time of waiting is to miss the point entirely. This was an age of profound seeing, where the human eye, trained by a lifetime of discipline, became the most advanced optical instrument on Earth. From the bustling markets of Baghdad to the quiet courtyards of monastic Europe, a global network of observers was at work. They did not peer into the void, they conversed with it, tracking the slow dance of planets against the fixed backdrop of stars with a patience we can scarcely comprehend today. Their tools were monuments to mechanical ingenuity. The Astrolabe, a handheld model of the universe cast in brass, could tell time, predict star positions, and solve complex problems of celestial geometry. The Armillary sphere, a skeletal globe of orbiting rings, made the abstract paths of the heavens tangible. These were not crude prototypes, they were the supercomputers of their day, encoding thousands of years of observational wisdom into elegant, portable devices. The drive for this knowledge was not abstract curiosity, it was woven into the fabric of survival and society. When would the Nile flood? When should seeds be sown? From which direction would the faithful turn in prayer? Which star would guide a ship safely to a distant port? Every question was answered by looking up. This intimate, daily reliance on the cosmos forged a relationship with the sky that was both practical and deeply philosophical. It was from this foundation of relentless, naked-eye observation that the first true maps of the heavens were drawn, not as artistic interpretations, but as engineering blueprints for understanding reality itself. Yet we rarely know their names. The first great mystery of this celestial renaissance is the identity of the mapmakers themselves. For every celebrated figure like the Persian scholar Abd al-Rahman Al-Ṣūfī, whose Book of Fixed Stars became a cornerstone of Islamic astronomy, there were hundreds of anonymous hands at work. These were the monks in cold scriptoria, meticulously copying star positions by candlelight. They were the court engineers in Baghdad or Samarkand, calibrating brass instruments to fractions of a degree. They were the scholars in the libraries of Oxford or Bologna, comparing observations across continents. Their legacy is not signed on paintings but etched into the very coordinates of the sky they helped define. This anonymity speaks to a profound difference in how knowledge was built. Ours is an age obsessed with individual credit, with singular genius. Theirs was a collective, centuries-long project. A single star chart might be the work of a lifetime, only to be refined by the next generation and the next in a slow, collaborative march toward precision. These individuals were not specialists in a narrow field. To map the heavens, one had to master geometry to calculate angles, mathematics to predict motions, and metallurgy to craft the perfect observational tool. They were, in every sense, the original polymaths, seeing the universe as a single, interconnected puzzle. Their greatest work was often unsigned, a selfless contribution to a cathedral of knowledge they would never see completed. So what tools did these anonymous builders use to take the measure of infinity? Their genius was not confined to ideas alone. It was forged in bronze and inscribed on parchment. To hold an astrolabe from this era is to hold a miniature universe, cold and heavy in your palm. Its creation was an act of profound translation, turning the vast, spherical dome of the night sky into a precise, flat disk of engraved brass. This was no simple tracing. It required the engineer to master a mathematical concept known as stereographic projection, a way of mapping points from a sphere onto a plane. Think of it as capturing the entire sky in a single, perfect shadow, preserving angles and relationships so that the tool remained truthful to the cosmos it represented. The craftsman had to calculate and engrave separate plates, thin brass discs etched with a spiderweb of coordinate lines, each one calibrated for a specific latitude on Earth. A traveler from Cordoba to Cairo would swap out one plate for another, reorienting his entire view of the heavens with a simple click of metal. The choice of materials was a deliberate act of defiance against time. They selected brass for its durability and resistance to corrosion, vellum for its longevity as a writing surface. These were not disposable tools. They were heirlooms of knowledge, built to be used for generations, to be passed from teacher to student, from one pair of curious eyes to the next. The engraving itself was an art form. Using fine chisels and meticulous punches, the craftsman would inscribe not just lines, but often beautiful Arabic calligraphy naming the stars, or intricate geometric patterns framing the functional data. This fusion was essential. The beauty invited contemplation, while the precision demanded respect. It signaled that understanding the cosmos was both a scientific and a deeply humanistic pursuit. But what guided the hand that held the engraving tool? What was the intellectual blueprint that told these artisans exactly where to place each star, each line on that waiting circle of brass? The true blueprint was written in the language of spheres. To translate the dome of the sky onto a flat disk of brass or a page of parchment, these engineers had to first master a form of mathematics that thinks in curves, not lines. This was spherical geometry, the science of shapes drawn on the surface of a ball. Every calculation, every engraved line on an astrolabe began with this fundamental truth. The cosmos was not a flat ceiling, it was a vast, rotating sphere, and to map it you had to learn its rules. This sophisticated knowledge did not emerge from a vacuum. It was preserved, refined, and brilliantly advanced by scholars in the Islamic world like Al-Battānī, whose meticulous observations corrected ancient Greek figures and provided a new level of numerical precision. Their work was the essential bridge, turning philosophical speculation into reliable engineering data. This mathematical framework was housed within a specific cosmic model, a grand architecture of the heavens that guided every prediction. The dominant view for over a millennium was the Ptolemaic system, named for the ancient astronomer Claudius Ptolemy. In this model, Earth rested motionless at the center of the universe. Surrounding it were a series of perfectly transparent, nested spheres, like the layers of a celestial onion. Each sphere carried a planet, the moon or the sun, while the outermost sphere held the fixed stars, turning once a day and painting the familiar arc of the night sky. We know today this model is incorrect, but to dismiss it as a simple mistake is to miss its profound ingenuity. It was a mathematically sophisticated and powerfully predictive machine. Using complex systems of circles upon circles, known as epicycles and deferents, Ptolemy's system could replicate the observed strange loops and pauses in planetary motions with remarkable accuracy. It was a clockwork universe built from geometry. This theoretical machine produced incredibly practical outputs, the planetary position tables known as Zijs. These were the software of the medieval cosmos, compiled by generations of astronomers. A Zij provided detailed, numerical data on where any planet or star would be on any given date. An engineer crafting an instrument did not need to derive every position from first principles. They could consult a Zij, a trusted compilation of centuries of collective observation, and use those numbers to engrave their brass with confidence. This is the crucial insight. Their achievement was not a collection of lucky guesses. It was a logical, systematic science operating within a consistent framework, using advanced mathematics to produce tools of stunning utility. Their world was centered on Earth, but their methods were rigorously celestial. Now, consider the challenge of taking this grand, spherical theory and compressing it into a single, handheld device that could be used by a sailor on a stormy deck or a scholar in a quiet courtyard. The solution was an invention of breathtaking elegance. The astrolabe was, in its essence, a universe you could hold in your hand. To call it a medieval smartphone is not an exaggeration of its role, only a translation of its purpose. It was the ultimate convergence device, a single tool that answered the most pressing questions of its time. Need to know the hour before sunrise, line up the sighting rule with a bright star. Need to determine your latitude for a sea voyage, measure the sun's height at noon, planning a building and want to align it precisely. The astrolabe could do that too. It even served as a calculator for complex problems in spherical astronomy, a skill that was the mark of a true scholar. Its operation was a beautiful physical ritual. You would suspend the brass disc from your thumb, letting it hang vertically. Then you'd pivot the sighting rule, a thin bar with tiny pinwheels for precise aiming, until you framed a star or the sun in its sights. With the instrument now oriented to the heavens, you'd look down at the front face. There, a delicate, lace-like framework called the rete would have rotated over a plate etched with coordinate lines. The rete was a star map in miniature, with pointers marking the positions of key celestial bodies. Where those pointers fell against the grid beneath them revealed the answer you sought. This was interactive technology at its most elegant, a direct dialogue between the user and a model of the cosmos. Its design was not static. Islamic craftsmen perfected the universal astrolabe, which could be used at any latitude. European makers added elaborate artistic flourishes, turning them into status symbols. Each culture that adopted it added layers of functionality, refining its accuracy and expanding its uses. For the sailor, it was a lifeline; for the scholar, a library; for the farmer, a calendar. This one object demonstrates the core philosophy of these engineers. They did not build a different tool for every single problem. They sought elegant, multifunctional solutions, creating a compact system that could unlock a vast array of answers from the consistent laws of the sky. Yet for all its portable brilliance, the astrolabe had limits. It was a model, a representation. To achieve the ultimate precision, to truly anchor the celestial map, these builders had to think on a monumental scale. They had to build the sky itself, fixed in stone. But to truly teach the cosmos, you needed more than a handheld model. You needed a universe you could walk around. The Armillary sphere was the master classroom of the medieval sky, a three-dimensional engine of brass rings that made the abstract architecture of the heavens physically tangible. If the astrolabe was a brilliant pocket calculator, this was the full-scale planetarium. Its design was a sculpture of pure theory. At its heart sat a small globe representing Earth. Surrounding it were a series of concentric rings, each one polished to a perfect circle, representing the great circles of the celestial sphere. One ring was the celestial equator, projected outward from our own. Another, tilted at an angle, was the ecliptic, tracing the sun's annual path through the constellations of the zodiac. Meridian rings marked north and south, while others could represent the horizon for any given location. These rings were mounted within a sturdy outer frame, often adorned with artistic flourishes, but engineered to rotate with silken smoothness. The larger versions, some standing as tall as a person, were not just display pieces. They were precision observational tools housed in dedicated observatories. A scholar could sight along a specific ring to measure the altitude of a star or planet, translating the brass model directly into fresh data. But its greatest power was pedagogical. a teacher could slowly turn the rings, demonstrating how the sun moved along the ecliptic through the seasons, or how the celestial equator shifted against the backdrop of stars. It made spherical astronomy visible. A student could see with their own eyes why the sun was high in the sky in summer and low in winter. They could understand the mechanics of solstices and equinoxes not as abstract dates, but as points where celestial paths intersected. The construction of such an instrument was a supreme test of an engineer's skill, crafting multiple large, perfect circles from metal, ensuring their planes were absolutely true, and mounting them on axles that allowed frictionless movement required the combined genius of a mathematician, a metallurgist, and a master jeweler. Each sphere was a monumental investment in time and resources, a testament to the value placed on comprehending the cosmic order. This desire to build a working model reveals a deeper truth about these engineers. They were not content with mere calculation. They hungered for comprehension, for a visceral, intuitive grasp of the celestial machine. The Armillary sphere was their ultimate expression of that hunger, a bold attempt to hold the skeleton of the universe in a human-made frame. Yet even this magnificent model was only as good as the data that informed its alignment. The perfect brass rings had to be set according to something. They needed to be calibrated against the only source of truth that mattered, the actual, ever-turning sky. This leads us to the most demanding discipline of all, the nightly vigil of the observer. The observer's work was a lifelong conversation with the night. Without the crutch of magnification, their greatest instrument was a cultivated, almost superhuman patience. A single astronomer might dedicate decades to tracking just one planet, like Mars or Jupiter, noting its position against the fixed stars night after night, year after year. They were mapping not a snapshot, but a slow, graceful dance, learning its rhythms by heart. To achieve precision, they relied on repetition and ruthless cross-verification. An observation made in Cairo would be compared with data from Cordoba or Marrakech. Consistency across continents and generations was the only true mark of accuracy. This demanded not just dedication but also monumental tools. Inside observatories, they built mural quadrants, giant stone or brass quarter circles fixed firmly to north-south walls. These were essentially protractors on an architectural scale. An observer would sight a star through a movable alidade along the quadrant's edge, and its angle could be read from the finely engraved scale with minimal error, eliminating the shake of a handheld device. The trained human eye became a sensitive detector in its own right. After a lifetime of practice, an observer could perceive the faintest change in a star's brightness or detect a subtle shift in a planet's path that modern eyes, accustomed to digital screens and light-polluted skies, might completely overlook. This discipline produced datasets of staggering longevity. Consider the work coordinated by Nasir al-Din al-Tusi at the Marrakech Observatory in the 13th century. Teams of scholars compiled observations into comprehensive tables, or Zijj, that became the gold standard for predicting celestial motions for over 400 years. Their legacy is a powerful reminder that technology can amplify, but it cannot replace the profound power of sustained, focused human attention. Yet this mountain of data, gathered over lifetimes and across empires, was just raw material. The true magic, the act of genuine creation, happened next. How do you transform 10,000 nightly notes into a single, definitive map of the heavens? The transformation from nightly notes to universal map was an act of supreme distillation. This raw data, the scattered whispers of the sky, was gathered and crystallized into the most powerful tools of the age, star catalogs and astronomical handbooks known as Zijj. Think of a Zijj not as a book, but as the living database of the medieval cosmos. Within its pages, you would find precise coordinates for hundreds of stars, tables predicting the future positions of planets, the sun, and the moon, and even information on eclipses. It listed not just where a star was, but often its brightness, what we call magnitude, providing a complete numerical portrait of the heavens. Creating such a work was a monumental feat of computation. It required applying spherical trigonometry to raw angular measurements, reducing thousands of individual observations into clean, predictable columns of numbers that a ship's navigator or a royal astrologer could use anywhere in the world. The most famous of these, like the Toledon tables compiled in Islamic Spain, or the later Alphonsine tables sponsored by King Alfonso X of Castile, became the standard reference works across Europe for centuries. They guided ocean voyages and reformed calendars, proving that data carefully compiled could reshape human endeavors. But perhaps their most beautiful feature was their inherent imperfection. A Zij was never truly finished. It was a living document passed from one generation of scholars to the next. A new astronomer with a sharper mural quadrant or a longer baseline of observations would discover a slight error in the predicted position of Saturn, or note a star that seemed slightly dimmer than the tables claimed. They would make their own annotations in the margin, or compile a whole new set of tables that incorporated these corrections. This was science as a slow, collaborative conversation across time, each generation standing on the shoulders of the last, gently nudging the collective map of the sky closer to truth. These catalogues were the essential translators, turning the silent language of the stars into actionable knowledge for princes, priests, and pilots. And it was this very knowledge that would soon be pressed into the service of one of humanity's greatest and most perilous adventures, the Age of Exploration. The star catalogue was not a dusty book, but a captain's most vital cargo. When European ships first turned their prows toward the open Atlantic, they sailed off the edge of the known world in more ways than one. Beyond the sight of land, the old rules of navigation died. There were no landmarks, no coastal currents to follow, only the vast, featureless desert of the sea. In this terrifying emptiness, the only fixed points were the sun by day and the stars by night. The celestial maps created by generations of patient engineers became the literal charts for crossing oceans. This was the ultimate field test for their science, and it demanded a new breed of rugged, simplified tools. The beautiful, delicate astrolabe of the scholar was too fragile for a storm-tossed deck. So craftsmen forged the mariner's astrolabe, a heavy, spoked wheel of brass, often weighted at the bottom. Its open design allowed the wind to howl through it without blowing it like a sail. A sailor would hold it aloft, line up the sun's beam through its sighting holes, and read the angle from a scale engraved directly on the metal. Another crucial instrument was the cross staff. Imagine a simple wooden staff with a sliding crosspiece. The navigator would place one end of the staff to his eye, slide the crosspiece until its top edge touched the sun and its bottom edge touched the horizon, and then read the angle from markings on the staff. It was crude, brilliant, and utterly dependent on knowing exactly where a given star or the noon sun should be in the sky for that date. That precise data came directly from the Zij, the astronomical tables. A navigator like Vasco da Gama carried with him the perpetual almanac of Abraham Zacuto, a Jewish astronomer who had compiled and perfected these tables. Zacuto's work translated the abstract coordinates of scholars into practical instructions for finding latitude. By measuring the height of the sun at its zenith and consulting Zacuto's tables, a captain could determine how far north or south of the equator his ship had traveled. It was a number, a single coordinate line drawn across the trackless ocean, but it was enough to grant a terrifying confidence. They could not yet find longitude, their east-west position, but knowing their latitude meant they could sail to a known parallel and then turn east or west to find their destination. This celestial guidance system enabled the voyages that redrew the map of the world. When Columbus set sail, he was using these very methods and tables. When Magellan's fleet completed its circumnavigation, It was a triumph of celestial navigation built upon centuries of pre-telescopic stargazing. The explorers expanded the known Earth, but in doing so, they also refined the known sky. Sailors venturing into the southern hemisphere reported constellations unseen by Ptolemy or Al-Ṣūfī. New stars were logged, and the celestial maps, once centered on the Mediterranean, slowly stretched to encompass the entire globe. The quest for better navigation drove a demand for even more precise astronomy, creating a feedback loop between the practical needs of the sailor and the theoretical pursuits of the scholar. The engineers who mapped the heavens had, in the most literal sense, built the compass for the modern age. Yet, for all this global expansion, a quiet revolution was brewing back in the observatories, one that would challenge the very center of their universe. The polished brass of an astrolabe tells a story of continents in conversation. To trace the lineage of a single star chart is to follow a path that winds from the libraries of Alexandria to the bustling translation houses of Baghdad, across the deserts of Central Asia, and into the quiet scriptoria of European monasteries. This was not a torch passed in a relay race from one civilization to the next. It was a sprawling, centuries-long symposium where scholars speaking Greek, Arabic, Persian, Sanskrit, and Latin all contributed to a single grand project mapping the heavens. The engine of this exchange was the Silk Road, but it traded in ideas more precious than silk or spice. When the Abbasid caliphs founded the House of Wisdom in Baghdad, they initiated a monumental effort of translation. Teams of scholars, often including Nestorian Christians and Jewish savants, worked to render the great works of Greek thinkers like Ptolemy into Arabic. But they did not merely copy the words, they questioned, corrected, and enhanced them, folding in sophisticated mathematical techniques from India and fresh observational data from Persia. This enriched knowledge then flowed westward. In the vibrant, multicultural cities of Al-Andalus, Islamic Spain, it reached new heights of practical engineering. Here, a figure like Al-Ṣūfī, known in Latin as Arzaschel, embodied the spirit of the age. He was not just a theorist, he was a master craftsman. He refined the design of the universal astrolabe, making it more accurate and easier to use, and his astronomical tables, the Toldon Tables, became a cornerstone for navigators and scholars for hundreds of years. His work, born in Cordoba, would be studied in Paris and used in Copenhagen, a testament to the borderless nature of curiosity. This interconnected web fundamentally reshapes our understanding of scientific progress. There was no single, sudden scientific revolution that sprang from Western Europe alone. Instead, there was a long, collaborative renaissance, a slow fusion of global intellect that built the foundation upon which Copernicus, Kepler, and Galileo would later stand. It was a process fueled not by dogma, but by a shared transcultural drive to solve the puzzles of the cosmos. And at the very heart of this global network were individuals whose personal journeys of synthesis produced works of staggering brilliance. Among the countless anonymous hands, a few brilliant names shine like fixed stars in the historical record, illuminating the collaborative nature of this great work. Abd al-Rahman al-Ṣūfī did not just compile data, he created a masterpiece of synthesis. His Book of Fixed Stars, completed in the year 964, was a conscious act of preservation and precision. For each of the 48 classical constellations, he provided two detailed drawings, one as seen from Earth and another as imagined on a celestial globe. More importantly, he listed each star's magnitude and position, but he did so by giving both its traditional Arabic name and its Greek counterpart from Ptolemy's Almagest. This was a deliberate bridge between cultures, ensuring that the star lore of the ancient world would not be lost, while anchoring it to the observational standards of his own time. His work became the definitive visual and textual guide to the night sky for centuries, a beautiful marriage of art and engineering. A generation before him, Al-Battānī had approached the heavens with a different, equally vital genius. Working from his observatory in northern Syria, he was less concerned with pictures and more obsessed with numbers. His lasting contribution was a relentless empirical correction of the past. By making more accurate observations over decades, he refined the values for the length of the solar year and the precession of the equinoxes, and he significantly improved the tables for the sun and the moon. Crucially, he advanced the use of trigonometric functions, moving astronomy from geometric models toward more powerful computational techniques. His work provided the sharper numerical tools that later mapmakers, including Al-Ṣūfī, would rely upon. The chain of transmission did not end in the Islamic world. Centuries later, in 15th century Europe, a German mathematician named Regiomontanus picked up the thread. His seminal text on triangles systematically laid out plane and spherical trigonometry for a European audience, providing the essential mathematical language for the coming astronomical revolution. Furthermore, he calculated new and improved ephemerides, tables of planetary positions that were more accurate than the aging Alphonsine tables. When Christopher Columbus sailed, he carried Regiomontanus's ephemerides with him, using them to interpret a lunar eclipse that awed the inhabitants of Jamaica. Each of these men, Al-Ṣūfī, the preserver and illustrator, Al-Battānī, the corrector and calculator, Regiomontanus, the systematizer and updater, represents a vital link. They did not work in isolation, but as dedicated nodes within a vast, centuries-spanning network. Their personal breakthroughs were only possible because they stood upon the compiled work of generations before them, and their own written legacies became the indispensable platform for those who followed. Yet this entire intellectual cathedral, this slow accumulation of precision, depended on a technology far more fragile than any brass instrument, the survival of the written word itself. Their knowledge survived because it was written in light. The fragile brilliance of the pre-telescopic universe was not preserved in stone or metal, but in ink and vellum, in the quiet, candlelit scriptoria of monasteries and the bustling royal workshops of kings. Here, the celestial blueprint was not just copied, it was reborn with each new manuscript, transformed into an object of both profound utility and breathtaking beauty. The most exquisite of these, like the Tres Riches Hures du Duc de Berry, were illuminated masterpieces. Amidst prayers and calendars, one could find intricately painted zodiac signs, golden stars scattered across deep blue heavens, and diagrams of planetary motions. The science of the spheres was literally gilded, reminding the viewer that understanding the cosmos was a sacred act, a way of glimpsing the divine order. This artistic fusion served a deeper purpose. The beauty made the knowledge precious, worthy of protection and preservation across generations. It ensured that a star chart was not a disposable tool, but a cherished heirloom, a treasure that would be safeguarded through times of upheaval. The scribe bent over his parchment was far more than a simple copyist. His task was an act of critical scholarship. As his quill traced the complex curves of an armillary sphere or the precise coordinates of a star table, he was engaging with the material. If a number seemed inconsistent with another source he had seen, he might annotate the margin with a question. If he had access to a more recent observation from a local scholar, he might incorporate it directly into the table, silently updating the work of a predecessor who had lived centuries before. This means every surviving manuscript is unique, a snapshot of astronomical understanding at a specific moment and place. A star catalogue from 10th century Baghdad will have subtle differences from one copied in 13th century Toledo, each bearing the fingerprints of its own era's corrections and curiosities. They are living documents frozen in vellum. Their survival is nothing short of a miracle of human dedication. These manuscripts endured the ravages of conflict, the threat of fire in wooden libraries, and the slow, silent decay of organic materials. They survived because individuals, often at great personal risk, chose to hide them, carry them to safety, or painstakingly recopy them as older versions crumbled. A single manuscript might be the last remaining thread connecting us to an entire observatory's lifetime of work. Today, these pages are our primary sources, the only way we can hear the direct whispers of the past. They sit in climate-controlled vaults in modern libraries, but when a historian opens one, they are not just reading text. They are deciphering a palimpsest of human endeavor, seeing the faint undertext of a corrected error, the careful hand of a monk who believed the stars were worth saving. But how do we, with our modern minds and technology, learn to listen to what these ancient pages are truly saying? The ink on those manuscripts is now being read by machines. Historians and astronomers today are engaged in a kind of celestial detective work, a field known as Archaeoastronomy. They take the star coordinates from a 1,000-year-old Zij, the faded numbers painstakingly copied by a monk, and feed them into sophisticated computer software. With a few keystrokes, they can rewind the sky, calculating exactly where those stars should have appeared on the night the original observation was made. This digital dialogue with the past often reveals a startling truth. The medieval measurements were not crude approximations. They were, in many cases, astonishingly precise. A worn brass astrolabe gathering dust in a museum cabinet holds a secret history in its engraved lines. By using a technique called astronomical dating, researchers can analyze the positions of the star pointers on its retear. Because the Earth wobbles very slowly on its axis, a motion called precession, the positions of the stars shift over centuries. By calculating when the star pattern on the instrument perfectly matched the real sky, scholars can often pinpoint the exact year and sometimes even the workshop where the astrolabe was made. It is a time machine built from mathematics. This ongoing rediscovery is far from over. New fragments of instruments are identified in forgotten museum drawers. Manuscripts long mislabeled in library archives are finally recognized for what they are: treasure maps to an older understanding of the cosmos. Each discovery adds another piece to the grand puzzle, helping us hear the voices of those ancient observers more clearly. This work creates a profound bridge across time, connecting a modern astrophysicist running a simulation with a medieval engineer squinting at a mural quadrant. They are separated by centuries but united in the same meticulous pursuit, measuring the universe to find their place within it. And in a beautiful twist, the data these engineers labored to collect is now helping to solve very modern problems. Their star charts hold a secret measurement of time itself, a hidden record of our planet's slow, celestial sway. This is the mystery of precession, the great wobble of Earth's axis. Like a spinning top beginning to slow, our planet's rotational pole traces a lazy circle in the sky over a cycle of 26,000 years. This imperceptible drift means the star we call Polaris, our North Star today, was not always the guide. In the time of the ancient Egyptians, the star Thuban in the constellation Draco marked the north, and in 12,000 years, the brilliant Vega will take its turn. The medieval engineers had no concept of a heliocentric solar system, let alone the gravitational forces that cause this wobble. Yet their star catalogues captured its effects with silent, meticulous fidelity. When Abd al-Rahman Al-Ṣūfī carefully recorded the exact position of a star like Spica in the year 964, he was unknowingly pressing a button on a stopwatch that would only be read a millennium later. Modern astronomers can take his coordinates, compare them to the star's position tonight, and measure the angular shift. The difference is a direct measurement of over 1,000 years of Earth's precessional drift. The precision of his naked eye observations, translated through spherical trigonometry and engraved into tables, provides a crucial data point in a timeline that no single human life could ever hope to observe. This is perhaps their most profound legacy, the gift of long-term data. They built a baseline of celestial positions against which all future change could be measured. Their work was not an end point, but a permanent marker in the river of time, allowing scientists today to calculate the rate of precession with greater confidence and to understand the long-term stability of our solar system. In this way, the engineers who mapped the heavens without telescopes are still active collaborators in modern astrophysics, their quill and brass instruments quietly correcting our understanding of a wobbling world. The principles that guided their hands are now written into the code of satellites. Look past the gleaming titanium and silicon of a modern space observatory, and you will find an ancient intellectual architecture. The Hubble Space Telescope does not simply float and stare, it must know exactly where to look. Its initial flaw, a microscopic error in the shape of its primary mirror, was a crisis of calibration. Correcting it required a series of precise adjustments, a process of iterative alignment not unlike an engineer slowly filing and testing an astrolabe's plates until the projected sky matched the real one. Both tasks demanded a mastery of geometry and a relentless pursuit of optical truth. The star catalogues that Hubble's computers consult to lock onto a target are the direct digital descendants of the handwritten Zyge. They are vast, searchable databases, but their purpose is identical: to provide a fixed coordinate grid against which everything else can be measured. This lineage extends to our footprints on other worlds. The sundial, one of humanity's oldest astronomical tools, found a new purpose on the surface of Mars. The Mars exploration rovers, Spirit and Opportunity, each carried a calibrated sundial known as the Mars dial. While it served a public outreach purpose, it also functioned as a fundamental calibration target for the rover's panoramic cameras, a nod to the most basic principle of using the sun's light to understand our place. Even the placement of massive radio telescope arrays, like the Very Large Array with its dishes arranged in a vast Y pattern, echoes the strategic alignment of ancient observatories to track celestial motions across the sky. This is not a coincidence. It is the logical evolution of a single, enduring idea that to comprehend the universe, we must first build reliable, precise instruments to extend our senses. The jump from a brass retet to a charge-coupled device sensor seems astronomical, but the intellectual leap was made centuries ago. It was the medieval mapmakers who established the rigorous framework, the culture of meticulous data and calibrated tools that made such a jump possible. Their greatest lesson is that technological revolutions are not sudden explosions, but the flowering of seeds planted long before. To grasp the full scope of their vision, we must temporarily set aside our own. There is a quiet experiment you can perform tonight to meet these engineers on their own terms. Find a patch of darkness away from the glaring streetlights, let your eyes adjust for 20 minutes, and look up. Do not reach for your phone. Instead, try to find the Big Dipper, that great celestial ladle swinging around the North Star. See the two stars that form the outer edge of its bowl. They are the pointers. Draw an imaginary line through them upward about 5 times the distance between them, and you will arrive at Polaris, the pivot point of the northern sky. Now, note the orientation of the Big Dipper's handle. Is it pointing upward like a question mark, or is it sweeping low to the horizon? This simple act, using one constellation to find another and reading the clockwork of the heavens, is the most direct link you have to the medieval observer. You are performing the same mental geometry, using the same fixed landmarks. This practice is called star hopping, and it is precisely how ancient navigators and modern amateur astronomers find their way to faint galaxies and nebulae. Without the instant gratification of an app, you must rely on memory, spatial reasoning, and patience. The sky ceases to be a random splash of glitter and starts to become a familiar, rotating map. Your perception of time stretches. You are not checking a digital clock. You are watching the slow, majestic turn of an entire sphere, a rhythm felt in your bones rather than seen on a screen. This simple exercise builds something more valuable than knowledge. It builds empathy. The engineers who mapped the heavens cease to be names in a history book. You begin to understand the chill of a long night's vigil, the frustration of a cloud passing at the crucial moment, and the profound satisfaction of finally confirming a star's position against your own handmade chart. Their monumental patience becomes relatable. Their skill feels human, not superhuman. They were practitioners, just as anyone who learns the sky today is a practitioner. This tangible connection makes their achievements resonate not as distant marvels, but as triumphs of focused human attention. Yet, for all we can reconstruct of their methods and admire in their tools, the historical record they left behind is tantalizingly incomplete, shadowed by gaps that spark debate among scholars to this day. The silence in the historical record is as telling as the words. For every beautifully preserved astrolabe displayed under museum glass, we must remember 100 others that met a more practical fate. In times of conflict or economic hardship, these intricate brass masterpieces were often seen not as treasures of knowledge but as raw material. They were melted down for coinage, for cannon, or simply repurposed into more mundane objects. The loss is incalculable. It is not just the instruments themselves that vanished, but the intimate knowledge of the hands that made and used them. Local observational techniques, ingenious shortcuts for calculation, and subtle refinements in craftsmanship often died with their practitioners, leaving tantalizing gaps in our understanding of how this science was truly practiced day to day. We read about the grand observatories, like the one built by the Timurid Prince Ulugh Beg in 15th century Samarkand. Contemporary accounts speak of a colossal sextant, a fixed arc carved into a hillside, so large it could measure the sun's position with unprecedented accuracy. But the structure itself is in ruins. While archaeologists can trace its foundations, the exact engineering of its sighting mechanisms, the full scope of its auxiliary instruments, and the precise daily routines of its observers remain partly in the realm of educated speculation. This physical absence forces historians to become forensic engineers. They must work backwards like detectives reconstructing a crime scene from a single fingerprint. A strange annotation in a star catalogue, an unexplained correction in a copied table, or an odd wear pattern on the only surviving example of a specific quadrant can become a crucial clue. These fragments are pieced together to reverse engineer lost methods, asking what problem were they trying to solve and what tool would logically have been used to solve it. This element of detective work makes the field vibrantly alive. A single discovery in a forgotten archive or a basement storage room can overturn decades of assumption. For instance, the identification of a previously mislabeled instrument as an Ottoman portable observatory can suddenly illuminate a whole new pathway of technological exchange. The most intriguing mysteries often involve the unexpected journeys of ideas. How did a particular design for an astrolabe repair, perfected in Persia, end up influencing workshops in Renaissance Germany? The paper trail is often missing, but the brass itself bears witness, its engraved stars telling a story of connection that no written chronicle recorded. This reality makes every surviving manuscript, every unbroken instrument, a minor miracle. They are not just artifacts, they are survivors, the lucky few that slip through the cracks of time to whisper their secrets to us. And sometimes the most profound secrets are not about the tools themselves, but about the revolutionary ideas they quietly helped to nurture, long before the world was ready to hear them. The star charts and brass instruments we admire today were not born from solitary genius, but from a very practical necessity: funding. Mapping the heavens was a staggeringly expensive endeavor. It required rare materials like high-quality brass and vellum, the full-time dedication of highly educated scholars, and the construction of dedicated observatories. This work could only flourish under the wing of powerful patrons, and the nature of that patronage profoundly shaped the science itself. Kings and caliphs were the venture capitalists of the medieval cosmos. A ruler like Alfonso X of Castile, known as Alfonso the Wise, poured vast resources into the translation of Arabic astronomical works and the creation of the Alphonsine tables. For him, this was not abstract curiosity. A precise celestial calendar was a tool of statecraft, vital for setting religious feast days, administering justice, and projecting an image of enlightened power. Astronomy was also the essential foundation for astrology, which was considered a serious science for guiding political and personal decisions. The patron's interests inevitably set the research agenda, directing minds toward calculating planetary positions for horoscopes or perfecting calendars for religious observance. Alongside royal courts, monasteries played an equally vital, quieter role. Within their walls existed one of the era's few stable, literate environments. Monastic scriptoria became factories for preserving knowledge, where monks meticulously copied and illustrated astronomical texts, ensuring their survival through turbulent times. The regulated daily life of a monastery also provided the perfect structure for long-term, consistent observation of the sky, turning the cloister into a kind of rudimentary research station. This system was the essential engine. Without a caliph funding an observatory in Marrakech or a wealthy merchant commissioning a master astrolabe, these engineering projects would have simply ground to a halt for lack of resources. It reveals a timeless truth that the pursuit of pure knowledge has always been deeply intertwined with the social, economic, and even spiritual priorities of its age. The patron provided the means, but the scholar provided the language, and that language itself was a marvel of engineering. The stars were not just points of light to be measured, they were characters in an ancient, ongoing story. To map the heavens was to engage in a profound act of naming, weaving cold coordinates into a warm tapestry of myth and memory that spanned continents. The very names we use for the brightest stars today are echoes of this medieval synthesis. Aldebaran, the follower, chases the Pleiades across the sky just as the Arabic name suggests. Betelgeuse, the giant's shoulder, marks Orion in a title derived from Arabic phrasing. Vega, the swooping eagle, carries its identity from the constellation Lyra. These are not arbitrary labels, they are linguistic fossils, preserving the precise moment when Islamic astronomers meticulously catalogued the heavens and gave these points of light identities that have endured for a millennium. This naming was a crucial layer of their engineering work. A coordinate is a number easily forgotten. A name, especially one tied to a vivid image or story, becomes a hook for the memory. It transformed the overwhelming scatter of stars into a recognizable cast of characters, making the complex celestial sphere navigable. The engineers compiling these catalogues were therefore also cultural linguists. When Abd al-Rahman al-Ṣūfī created his Book of Fixed Stars, he did not impose a single tradition. For each constellation, he presented both the Greek mythological figure, like Hercules or Andromeda, and the corresponding Arabic visualization, often an animal or everyday object from Bedouin life. He might note that the stars we see as the twins Castor and Pollux were seen by Arab observers as a pair of peacocks. This was not confusion, it was deliberate, scholarly translation. He was building a bridge of understanding, ensuring that the star lore of Persia, Greece, and the Arab world could coexist and inform one another within a single, precise scientific framework. This fusion had a practical genius. The mythology provided a sturdy, memorable skeleton. Anyone learning the sky could remember that the hero Perseus held the head of Medusa, and the star Algol, whose name means the demon's head, winks within that constellation, marking the ghastly trophy. The story gives context to the flicker, making the variable star's behavior part of a larger narrative. This layered approach meant their celestial maps were never sterile documents. They were rich cultural palimpsests where the mathematics of spherical geometry shared the page with tales of epic quests, celestial animals, and ancestral heroes. This blend of measurement and meaning did not stay confined to the scholar's library. It spilled out into the broader culture, illuminating manuscripts, guiding the symbolism in royal tapestries, and even determining the alignment of sacred architecture. The stars, named and storied, became a shared vocabulary for art, poetry, and spiritual contemplation, proving that the engineers who mapped the heavens were also quietly mapping the human imagination. The cosmos they mapped did not stay confined to the observatory. It spilled out in radiant color and carved stone to become the visual language of an entire age. In the luminous frescoes of Renaissance Italy, the deep blue vault of a church ceiling is often studded with perfect golden stars, arranged not randomly, but according to the latest celestial charts. This was more than decoration, it was a declaration. The ordered, predictable universe, meticulously documented by the engineers, served as the ultimate symbol of divine harmony. In a painting of the Nativity, the precise constellation overhead was a silent testament to a cosmos governed by rational law, a fitting backdrop for the moment of divine incarnation. This artistic integration made the celestial architecture tangible for every worshipper, a daily reminder that heaven itself operated on principles of exquisite geometry. Literature, too, was infused with this cosmic precision. Geoffrey Chaucer, better known for his Canterbury Tales, also authored a treatise on the Astrolabe for his young son. This was not a dry manual, but a gentle, paternal guide to understanding the world through this instrument of brass and shadow. By explaining its use, Chaucer was doing more than teaching astronomy. He was passing on a framework for seeing time, space, and human life as interconnected parts of a grand system. The astrolabe in his hands became a bridge between the practical and the philosophical, a tool for a poet as much as for a sailor. Perhaps the most profound integration occurred in architecture, where faith was literally built upon astronomical principles. Consider the breathtaking octagon tower at Ely Cathedral in England. After the original central tower collapsed in the 14th century, the builders did not simply replace it. They constructed a vast, 8-sided lantern, a structure of staggering ambition that seemed to defy gravity. While not a functional observatory, its design resonates with cosmic symbolism. The number 8 evoked renewal and resurrection, and the lantern itself, flooding the sacred space below with light, acted as a monumental conduit between the earthly church and the heavenly firmament. The alignment of certain cathedrals to capture the light of the equinox sunrise, or the celestial patterns laid into mosaic floors, all whispered the same truth. The builders saw the house of God as a microcosm of his perfectly ordered creation. This cultural permeation reveals the true scale of the engineers' achievement. Their work provided more than data, it provided a foundational metaphor. The predictable clockwork of the spheres became a model for a harmonious society and a structured, comprehensible faith. In a world often filled with uncertainty, the unwavering cycles of the heavens offered a template for stability, law, and divine reason. Astronomy was not a niche pursuit for specialists. It was a central pillar of intellectual life, a lens through which everything from governance to theology was viewed and understood. The entire medieval worldview, in many ways, was built upon the celestial map they had so carefully drawn. Yet, even as this vision reached its most beautiful and integrated peak, the first cracks in its foundation were beginning to appear. A single, persistent anomaly in their perfect system was about to trigger a revolution that would dismantle the cosmic order they had so brilliantly documented. The polished certainty of the medieval cosmos was about to meet a lens. When Galileo first turned his telescope toward Jupiter in the winter of 1610, he saw something utterly unexpected: 4 tiny points of light dancing in a line near the giant planet. Night after night, their positions shifted, not wandering freely like stars, but clearly orbiting Jupiter itself. This simple observation did more than just discover new moons. It delivered a profound shock to the established order. Here was a miniature solar system in motion, with a center that was not Earth. The telescope, that ingenious tube of glass and lead, was suddenly revealing a universe far more complex and crowded than the naked eye had ever suggested. It showed mountains on the moon, turning a perfect celestial sphere into a rugged, Earth-like world. It revealed the phases of Venus, which could only be explained if Venus was orbiting the Sun, not Earth. These were discoveries that shook the foundations of the Ptolemaic model to its core. Yet, for all its revolutionary power, the telescope was utterly lost without the work that came before it. Galileo did not point his instrument into a random patch of darkness and stumble upon Jupiter. He knew exactly where to look because of the precise planetary tables, the Zyges, compiled by generations of pre-telescopic astronomers. The coordinate system they had built, the very map of the heavens etched into brass and parchment, was the only thing that gave the telescope direction. Their star catalogues provided the fixed background against which these new, wandering points of light could be tracked and their orbits calculated. The mathematical language of spherical geometry, refined by scholars like Regiomontanus, was the essential tool for making sense of what the telescope revealed. So the story is not one of erasure, but of acceleration. The engineers had built the roadmap. The telescope simply allowed travelers to see the previously invisible landmarks along the way. This continuity is perfectly embodied in the surprising afterlife of their most iconic instrument. Even as telescopes spread across Europe, the humble astrolabe did not vanish into museums. It remained in active use for navigation well into the 18th century. Its principles now guiding ships that were crossing oceans charted with the help of the very celestial phenomena the telescope had uncovered. The old tools and the new technology existed in a necessary partnership, one providing the foundational grammar, the other writing startling new sentences in the book of the sky. The astrolabe outlived its practical necessity because it taught something a telescope never could: the underlying geometry of the sky itself. Long after sailors relied on sextants and astronomers peered through lenses, this ancient instrument found a permanent home in the classroom. Its enduring power lies in its tangible truth. A student can hold the brass disc, feel the weight of the rete as it rotates, and see with their own hands how the sun's path shifts with the seasons. This physical interaction turns an abstract celestial sphere into a mechanical puzzle they can solve, making concepts like declination, right ascension, and the ecliptic plane not just terms to memorize, but relationships to physically manipulate. The connection between a flat, two-dimensional star chart and the three-dimensional dome overhead becomes an experience, not just an explanation. This is why modern educators, even with access to stunning digital simulations, still reach for replica astrolabes or classroom kits. There is a cognitive leap that happens when theory is held in your palm, a leap that a screen, for all its beauty, cannot always replicate. Planetarium software often includes virtual astrolabes for this very reason, using interactive models to guide visitors through the same logical steps a medieval scholar would have followed. The instrument's design is a masterclass in didactic engineering. Every engraved line, every rotating part, exists to reveal a relationship. It teaches a systematic, spatial way of thinking, training the mind to translate between a local horizon and a universal coordinate grid, to think in curves and angles. This cognitive toolkit, forged in medieval workshops, is fundamentally about problem solving. It is less about memorizing where a star is, and more about understanding how you would find it, or tell time by it, or navigate with it under any conditions. In this way, the astrolabe's greatest legacy may be pedagogical. The engineers who mapped the heavens gifted us not only a map, but a method for reading all maps. They embedded a way of seeing into brass and vellum, a process of inquiry that begins with observation, proceeds through geometry, and culminates in a usable model of reality. This timeless approach to learning connects directly to the modern scholars who now work to preserve the very objects that taught it. A museum conservator's lightest touch could still erase a star's position forever. This is the delicate paradox faced by those who protect the surviving instruments today, where the very act of study risks damaging the irreplaceable artifact. To solve this, institutions have turned to a suite of non-invasive technologies that feel almost like magic. X-ray fluorescence can reveal the exact composition of the brass, telling us where the metal was mined and how it was alloyed without taking a single sample. High-resolution, three-dimensional scanning captures every scratch, every engraved line, and every subtle warp in the metal, creating a perfect digital twin. This twin becomes something extraordinary, a virtual instrument that anyone, anywhere in the world can now rotate, zoom into, and even manipulate online. You can align the repair of a virtual astrolabe from the comfort of your home, performing the same calculations a medieval scholar would have, feeling the click of virtual brass that you never risk touching. Projects like the Warburg Institute's vast digital archive are compiling thousands of these celestial images from fragile manuscripts, creating a global library that fire or decay can never threaten again. This digital resurrection does more than preserve, it democratizes. Knowledge that was once locked in a prince's treasury or a monastery's restricted scriptorium is now a click away for a student in Buenos Aires or an enthusiast in Seoul. It is a profoundly fitting new chapter in this story, using 21st century networks to honor 10th century ingenuity, ensuring the conversation they started continues. And for a growing number of artisans, this digital blueprint is not an end but a beginning. They are using these precise scans as guides to do something remarkable, to bring the crafts themselves back to life. The modern astrolabe begins not with brass but with a question. What did it truly feel like to hold the chisel? A dedicated community of artisans, historians, and engineers around the world is now answering that question not through theory, but through the heat of the forge and the scrape of the engraver's baron. They are not simply making copies, they are performing a meticulous act of resurrection, using only the tools and techniques available to a medieval craftsman. Their primary guides are the very manuscripts and surviving instruments we have been discussing. They pore over Chaucer's treatise on the astrolabe, not just for its instructions, but for the subtle assumptions it makes about the reader's knowledge. They analyze the microscopic tool marks on a 500-year-old quadrant in a museum case, looking for the specific angle of the engraver's cut or the telltale signs of hand filing. Every decision, from the composition of the brass alloy to the type of charcoal used in the casting pit, is a historical puzzle to be solved. This painstaking process is a form of experimental archaeology, where the recreation of the object becomes a journey into the mind of its maker. The artisan is no longer a distant observer, but a collaborator across centuries, facing the same material constraints and technical headaches. They discover that the beautiful curves of the repair are not just aesthetic, they are a practical necessity to provide structural strength to the delicate brass web. They learn that aligning the sighting rule perfectly requires an intuitive feel for spherical geometry that no written manual fully captures. This hands-on work reveals the invisible craftsmanship, the countless micro-decisions a master made that were never written down because they were simply part of the tradition, passed from master to apprentice in the workshop's quiet hum. The most profound revelations often come from failure. A lost wax casting might bubble and pit, ruining a day's work, revealing the precise temperature and alloy mix the ancients perfected through trial and error. Hand engraving a degree scale on a curved plate teaches the immense discipline of the hand and eye, where a single slip means starting over. Through these struggles, the medieval engineer ceases to be an abstract genius and becomes a relatable practitioner, a problem solver covered in metal dust. The modern artisan, by walking the same path, bridges the immense gap between seeing a finished instrument under glass and understanding the lived experience of creating it. This revival does more than produce stunningly beautiful and accurate replicas. It forges a tangible, empathetic link to the past. It asks us to consider not just what these individuals knew, but who they were, patient, resilient, and deeply connected to the physical world through the work of their hands. Their work required a psychology of profound patience, a willingness to measure the universe 1 degree at a time. The medieval engineer's most vital attribute was not a tool, but a temperament. They understood that truth accretes slowly, like the finest layers of varnish on an instrument, built from 10,000 nights of observation and correction. A single star's position might be refined across 3 generations, each successor trusting the data of the last while adding their own minute adjustment. This long now thinking stands in stark contrast to our world of instant updates. For them, a project's worth was measured not in quarterly results, but in its potential usefulness a century hence. This patience was married to a voracious, cross-disciplinary curiosity. The same mind that calculated the angle of the ecliptic also needed to understand the behavior of molten brass in a mold, the tensile strength of a sighting rule, and the aesthetic principles that would make a complex diagram feel intuitively beautiful. They did not see barriers between science, art, and craft. They saw a single continuum of making and knowing. The astrolabe is the perfect emblem of this fusion, a mathematical proof rendered in engraved metal, designed to be both functionally flawless and visually magnificent. This unity of purpose points to a fascinating intellectual humility, often expressed in their own writings. A scholar would routinely attribute a new discovery to the grace of God, or frame his own work as merely a clarification of a great predecessor like Ptolemy. This was not a lack of confidence, but a cultural framework that placed individual insight within a grand, collaborative tradition stretching back to antiquity. Yet within that accepted framework, they were relentless, bold innovators. They corrected Ptolemy's numbers while praising his name. They redesigned instruments for new purposes, invented new projection methods, and compiled data that quietly undermined the very cosmic models they publicly upheld. Their drive for precision became a kind of spiritual pursuit. There was a beauty perceived in a perfectly calibrated scale, in a star catalogue where every number aligned, in the silent click of a rete settling into its correct position. Accuracy was not just practical, it was a form of reverence for the ordered cosmos they believed in. This mindset, this blend of patience, interdisciplinary synthesis, humble collaboration, and reverence for precision, offers a quiet antidote to our own age. Cultivating a fragment of their deep focus, their willingness to think across boundaries, and their respect for meticulous craftsmanship can transform how we approach problems today, whether writing code, restoring an ecosystem, or simply learning a complex skill. To study their instruments is to admire their engineering, but to understand their mindset is to learn their philosophy. And this philosophy was invariably directed toward solving puzzles of breathtaking complexity, often with stakes that were both celestial and deeply human. Their celestial clock was flawed, and they knew it. A sundial's shadow, that ancient and trusted marker of noon, could not be relied upon for perfect timekeeping. The discrepancy has a precise name, the equation of time. It is the difference between apparent solar time, measured by the sun's actual position in the sky, and mean solar time, the steady, average tick of a mechanical clock. Over the course of a year, a sundial can run up to 16 minutes fast or slow compared to a uniform clock. This was not a minor error. For a scholar calculating prayer times or an astronomer timing an eclipse, those minutes mattered immensely. The cause is twofold: the elliptical shape of Earth's orbit, which makes our planet speed up and slow down as it travels around the Sun, and the tilt of Earth's axis. These two celestial rhythms combine to create a complex, wavy pattern of daily discrepancy, a signature of our planet's dance in space. Medieval engineers had no concept of elliptical orbits or gravitational mechanics as we understand them. Their cosmic model was one of perfect circles, yet through meticulous, long-term observation, they detected this subtle wobble in time itself. They could see the effect long before they could explain the cause in modern terms. Their genius was to measure the symptom and engineer a cure, all within the elegant constraints of their spherical universe. They embedded the solution directly into the brass of their most sophisticated instruments. On certain astrolabes, you can find a curious, often serpentine scale engraved along the rim, sometimes labeled the equation of time scale. This was not a standard feature, it was an advanced module, a specialized hack for the cognoscenti. To use it, an observer would first determine the apparent solar time from their astrolabe or sundial. Then, they would find the current date on the equation scale, which would indicate a correction value, a number of minutes to either add or subtract. Applying this correction yielded mean solar time, the uniform time needed for accurate tables and predictions. Creating this scale was a monumental feat of geometrical analysis and data compression. It required folding an entire year's worth of observed solar discrepancies into a single, continuous curve on a small metal disk. This curve was a graphical representation of a natural law they could not yet name, a silent map of Earth's elliptical journey encoded in brass. This achievement reveals a profound layer of their sophistication. They were not merely recording the positions of static stars, they were modeling dynamic, non-uniform motion. Their geometrical approach, while based on the wrong physical model of circular orbits, produced a functionally correct solution for the problem at hand. It was a brilliant workaround, a testament to their principle that a useful approximation derived from rigorous observation could be more powerful than a beautiful but impractical theory. They saw the puzzle in the data and engineered a tool to solve it, showcasing an empirical flexibility that is the hallmark of great practical science. The equation of time scale is a quiet masterpiece of problem solving, a visual algorithm etched in metal that allowed a user to harmonize the sun's irregular heartbeat with the steady pulse of human-made time. A finely engraved astrolabe often held more than just coordinates. Beyond the precise scales and star pointers, the blank spaces on the brass were a canvas for personal identity and hidden purpose. A craftsman might inscribe a short prayer for divine guidance in elegant Arabic calligraphy along the rim, or a Latin motto praising God's orderly creation. The owner's name, sometimes accompanied by a coat of arms, declared this instrument a personal possession, a treasure to be passed down through a family. Zodiacal symbols, beautifully rendered, were not merely decorative. They anchored the tool to the cyclical nature of time and human fate, blending scientific and astrological use into a single object. Some engravings served as subtle codes. A series of numbers near the throne, the instrument's hanging ring, might not correspond to any obvious star position. Historians have found that these can be cryptic references to a specific city's latitude, a kind of secret signature for the workshop that made it, or even numerical values tied to mystical philosophical systems, embedding a layer of esoteric knowledge for the initiated user. These details transform the object. An astrolabe commissioned for an Ottoman sultan, for example, would likely be lavishly decorated with floral patterns and gilding, but its most telling feature might be a finely engraved Qibla indicator, a scale dedicated to finding the precise direction of Mecca from any location. This single addition shifts the instrument's story from a general tool of astronomy to a deeply personal artifact of faith and devotion for a specific ruler. It tells us that for its owner, understanding the cosmos was inseparable from fulfilling religious obligation. Every scratch, every choice of symbol, every dedicatory phrase turns a mass-produced scientific device into a unique biographical document. It whispers about the person who held it, what they believed, and what they sought from the stars. This intimate connection between maker, owner, and cosmos makes the inevitable flaws we find in these instruments not failures, but profoundly human signatures. Their star charts were not always perfect. A close look at the surviving manuscripts reveals slips of the pen. A star plotted a degree too far east, or a planetary position calculated for the wrong hour. These documented errors are not signs of failure. They are precious windows into the real human process of discovery. In the margins of a copied zij, you might find a tiny, neat note in a different hand, a later scholar gently pointing out a discrepancy they had observed. One manuscript might list a star's magnitude as 3, while a copy made 50 years later, based on fresh observations, corrects it to 4. This is the sound of science listening to itself, a slow, critical conversation across generations. The value of an error lies in its correction. Take the predicted timing of a solar eclipse. Early medieval tables might be off by several hours, a dramatic miss. But as centuries passed, as observations accumulated and mathematical techniques refined, those predictions grew sharper and sharper. By the late medieval period, scholars could often predict an eclipse within a matter of minutes. This steady, upward curve of accuracy is the true story, not any single perfect prediction. It shows a community engaged in a collective project of refinement, where each astronomer's work served as a benchmark for the next to test, challenge, and improve. This process often spanned continents. An astronomer in Cairo might read a star catalogue compiled in Persia and notice a star's position did not match his own nightly records. He would not dismiss the Persian work, he would annotate it, creating a hybrid document that carried both the original data and the new insight. His correction might then travel to Spain, where another scholar would incorporate it into a new set of tables. Knowledge flowed along these intellectual trade routes, constantly being filtered and purified by critical minds. Acknowledging their mistakes makes these engineers profoundly relatable. They were not infallible sages receiving truth from the heavens. They were brilliant, persistent problem solvers working with imperfect tools and incomplete data. They struggled with cloudy nights, with the limitations of human eyesight, and with the inherent complexity of the models they used. Their ultimate achievements, the breathtakingly precise instruments and maps we admire, emerged from this honest, gritty struggle. They impress us not because they were always right, but because they built a system designed to find out when they were wrong and to fix it. This self-correcting mechanism, embedded in the very culture of their scholarship, is perhaps their most modern and enduring gift. It reminds us that the map of knowledge is never finished. It is always being redrawn, one careful correction at a time. A question could travel faster than a person ever could. Across the vast deserts and stormy seas of the medieval world, a quiet, relentless postal service was in operation, one that carried not spices or silks, but celestial coordinates and philosophical debates. This was the Correspondence network of the astronomers, a slow-motion conversation that wove together the intellectual capitals of the age. A scholar in Cairo, puzzled by an anomaly in the orbit of Saturn, would compose a detailed letter. That letter would be entrusted to a caravan bound for Damascus, then perhaps a ship sailing to the ports of Al-Andalus, finally reaching the desk of a fellow expert in Cordoba months later. After contemplation and local observation, a reply would begin the long journey back, often accompanied by freshly copied pages of astronomical tables or meticulous diagrams for a new instrument design. This was collaboration measured not in minutes but in seasons. The content of these letters reveals a community built on mutual need and deep respect. We see this in the surviving correspondence of figures like Johannes Regiomontanus. He did not work in a vacuum in his Nuremberg workshop. He actively wrote to colleagues across Europe requesting very specific data. He might ask an astronomer in Rome to observe the exact time the moon passed a certain star on a particular night, or someone in Vienna to measure the altitude of the sun at the solstice. He needed these observations from different latitudes to triangulate his calculations, to refine the grand celestial map. Each letter was a node in a vast, human-powered computing network, pooling scattered eyes and minds into a single, distributed observatory that spanned the continent. This system functioned as the medieval internet, a vital infrastructure for knowledge exchange that operated at the speed of a horse or a sail. Its protocols were trust and scholarly reputation. Its currency was meticulously copied data and constructive critique. A new set of planetary tables compiled in Persia would ripple outward through this network, being tested, annotated, and corrected in India, the Maghreb, and eventually Christendom. An innovative astrolabe design perfected in Aleppo might find its way into a workshop in France a generation later, its journey documented only in the silent similarity of brass. This decentralized model had a profound strength. No single library fire, no conflict in one region could erase the collective knowledge. It existed in dozens of copies, in hundreds of minds, scattered across the known world, constantly being updated and verified through this ongoing conversation. The pace was glacial by our standards, but the acceleration it provided was immense. A problem that might have stalled a lone scholar for a lifetime could be circulated to a dozen of the keenest minds on 3 continents. Someone somewhere might have already observed the key event or derived the necessary geometry. This network turned individual curiosity into a collective project. It underscores a timeless truth about discovery, that the engine of progress has rarely been the isolated genius in a tower. It is, and always has been, the connected community, the shared puzzle, the willingness to send a question out into the world and wait with patient hope for an answer to return. Through ink and parchment, these engineers built a web of minds, all focused on the same magnificent goal, to decode the mechanics of the night. And that collective project was ultimately driving toward answers for humanity's most enduring questions. The brass instruments and star charts were ultimately questions cast in metal and ink. Each precise measurement, each carefully engraved line, was a search for something far greater than coordinates. It was a search for order in a world that often felt chaotic, for evidence of a divine architect behind the silent, majestic turn of the spheres, the predictable return of the seasons, the unwavering paths of the planets. These were not just mechanical facts to the medieval mind. They were the clearest possible proof of a cosmos built on reason, a universe singing in geometric harmony. This belief was the silent fuel for centuries of work. Why spend a lifetime tracking Jupiter's loops? Because in its perfect, predictable cycle, you were glimpsing the mind of the Creator. The celestial map was, in their eyes, a direct reflection of divine intelligence, and to chart it was an act of devotion, a form of prayer written in mathematics. This philosophical drive connected every aspect of their endeavor. The monk in his scriptorium, the engineer at his forge, the scholar calculating an eclipse, all were participants in a unified quest. Knowledge of the physical world was not separate from spiritual understanding. It was the very path to it. To comprehend the cosmos was to draw closer to its source. This is why their work was infused with such reverence for precision. A perfect astrolabe was not just a useful tool, it was a worthy offering, a mirror held up to a flawless creation. Their entire framework, from the nested spheres of Ptolemy to the elegant scales on their instruments, was built on this foundational idea of a rational, purposeful universe. Our modern cosmology tells a vastly different story of expanding space, dark energy, and a solar system adrift in a galaxy among billions. Yet the core human impulse that drove those ancient observers remains utterly unchanged. We still look up at the night sky with the same yearning, the same need to ask where we belong in the grand scheme of things. We may no longer see the hand of a divine clockmaker in the orbit of Mars, but we feel the same awe, the same humble curiosity. Their quest was for a celestial order that reflected divine reason. Our quest is for underlying physical laws, for a theory of everything. The language of the search has transformed, but the longing behind it is a direct, unbroken line from their time to ours. To honor their work is to recognize this shared motivation, to see in their patient stargazing not just a historical artifact, but a profound expression of a timeless human need to find our place in the vastness and feel, somehow, at home. The master instrument maker of the 14th century would recognize the modern software engineer's deepest challenge. Both face the same fundamental task, translating an abstract, complex system into a clear, usable tool for others. The astrolabe was not just a map of stars, it was an interface designed to make the overwhelming data of the cosmos accessible to a navigator or a student. Its elegance came from ruthless simplification, presenting only the most essential information through an intuitive, physical interaction. Today's most successful digital platforms strive for this same clarity, hiding immense complexity behind a simple, engaging user experience. This is the first lesson, the power of a brilliant interface. Whether crafted from brass or code, the best tools feel inevitable, as if they were always meant to work exactly that way. Their methodology was inherently interdisciplinary, a fusion we now call systems thinking. The instrument maker had to be part mathematician, part metallurgist, and part artist. The success of the final astrolabe depended on each discipline informing the others, the beauty making the mathematics inviting, the precise mathematics guiding the artist's engraving hand. Modern projects, whether launching a satellite or developing a new vaccine, demand this same synthesis of expertise. Siloed teams create fragile solutions, while integrated collaboration builds resilience. The medieval workshop, where theory and practice were in constant conversation, models the kind of agile, cross-functional environment that solves our most wicked problems. Perhaps their most profound gift to us is the concept of the long data set. The Zij, those meticulously maintained astronomical tables, were not disposable reports. They were living documents, curated and corrected over centuries, each generation adding a layer of precision to the last. In our era of digital archives that can become obsolete in a decade, their commitment to durable, portable, and transparent data is a stark reminder. They built knowledge to last using formats like standardized numerical tables that any scholar in any culture could interpret and build upon. Our modern challenge is to design digital systems and data protocols with that same foresight, creating information legacies that will remain accessible and useful for generations we will never meet. This work required a psychology of deep patience, a willingness to invest in projects whose full value might not be realized for 100 years. We live in an age of rapid iteration and quarterly results, where the quick fix is often prized over the durable solution. Their example asks us to recalibrate. Some problems, like climate change or foundational scientific research, cannot be solved in a single funding cycle. They require the kind of sustained, collective focus that built the celestial catalogues, where progress is measured not in leaps, but in the slow, relentless accumulation of tiny, verified improvements. True innovation is often a slow bloom, not a sudden flash. Finally, they teach us that constraints are not the enemy of creativity, but its catalyst. The medieval engineer had no precision lathes, no digital simulations, no electricity. Their materials were brass, wood, and vellum. Their power was human muscle and focused sunlight. These limitations forced a radical elegance. Every component of an astrolabe had to serve multiple purposes. every calculation had to be optimized for hand execution. This scarcity bred ingenuity. In our world of seemingly limitless computational power, we can sometimes engineer solutions of overwhelming complexity that are fragile and difficult to maintain. Their legacy whispers a question: what is the simplest, most robust, and most beautiful way to solve this? It is a call to value durability over novelty, clarity over cleverness, and to build not for the next product launch, but for the slow, steady arc of human understanding. The archive doors are still opening. While we have pieced together a remarkable story from the manuscripts and instruments we know, the true scale of the medieval celestial project remains hidden. In the deep vaults of libraries from the Vatican to Istanbul, and in the storerooms of museums from Cairo to Delhi, thousands of uncatalogued manuscripts wait in quiet obscurity. Each one is a sealed envelope from the past, potentially containing an unknown star chart more detailed than any we have seen, a set of engineering drawings for a lost instrument, or a personal observational diary filled with nightly notes that could rewrite a chapter of astronomical history. These are not merely duplicates of known works, they are the undiscovered country of pre-telescopic science. A single, fragile volume, mislabeled centuries ago as a book of prayers or poetry, could be the sole surviving record of an entire observatory's work, a data trove that connects observations from Baghdad to Beijing. The next great discovery in this field may not come from a new telescope pointed at the stars, but from a scholar's careful hands turning a previously ignored page in a centuries-old library ledger. This is the thrilling reality. The map of this history is still being drawn, and its blank spaces are vast. Alongside these paper treasures, the earth itself holds secrets. New archaeological excavations, whether at the site of a forgotten monastery or within the foundations of an ancient university, could unearth more instruments. Imagine a cache of brass astrolabes buried for safety during a long-ago conflict, waiting to be found, or the discovery of a master craftsman's workshop with half-finished tools and molds, revealing the step-by-step process of creation in a way no finished object ever could. Each piece of tarnished metal pulled from the ground is a new voice added to the conversation, offering physical evidence of trade routes, technological transfer, and personal skill that manuscripts alone cannot provide. To read these objects, we now wield tools the original engineers could never have dreamed of, yet would have deeply admired for their precision. Multispectral imaging, a technique that uses different wavelengths of light, can peer beneath the surface of a vellum page. It can resurrect ink that has faded to near invisibility, bringing a star's coordinate back from the brink of oblivion. More astonishingly, it can reveal palimpsests, manuscripts where the original text was scraped away so the precious parchment could be reused. To the naked eye, you see a medieval legal document or a later theological treatise. Under the multispectral camera, the ghostly undertext emerges, perhaps the lost draft of a famous astronomer's calculations or the private notes of a lesser-known scholar. This technology is a time machine, allowing us to recover works that were literally erased from history, giving us a second chance to hear voices that were silenced. Every one of these potential discoveries, whether on parchment or in the soil, carries the same profound promise. It adds nuance, correcting our broad assumptions with specific, local detail. It might introduce us to a completely forgotten engineer, a woman or a man whose name was lost but whose meticulous work survives. It could reveal a collaborative network we never knew existed, a letter tucked into a binding that shows a correspondence between thinkers we assumed worked in isolation. This means the history you are learning about right now is actively being written and rewritten. You are not receiving a settled, dusty narrative from a sealed book. You are witnessing a live excavation of the intellect, a real-time recovery of a lost golden age of cosmic engineering. The contributions of these pre-telescopic pioneers are coming into ever sharper focus with each passing year, as new technologies meet old archives and curious minds ask new questions of the past. Their story, therefore, is not a completed monument. It is a living, growing tapestry, and we are all here together, watching as its next brilliant threads are carefully woven back into the light. The brass astrolabe you might see in a London museum carries a map drawn in Baghdad, a story copied in Cordoba, and a journey that ended with an empire's reach. This simple truth forces a modern question that has no easy answer: who truly owns the stars, or at least the human genius that once mapped them? The physical legacy of these engineers is scattered across the globe, a direct reflection of history's complex tides. A priceless manuscript penned in a Timurid workshop now rests in a European library. A masterfully engraved instrument from Damascus is displayed under glass in a North American gallery. Their dispersal is rarely a simple tale of scholarly exchange. It is often interwoven with the harder narratives of colonial acquisition, where knowledge, like territory, was gathered and catalogued under a new flag. This scattering creates a poignant disconnect: the cultural and intellectual context that gave birth to these objects, the world of the scholar in his observatory garden, the sound of the scribe's pen in a royal library, feels distant when viewed through a museum case far from home. It raises a profound ethical dimension to our rediscovery. Celebrating this global genius is one thing, but stewarding its physical legacy with respect for its origins is another challenge entirely. One promising response to this challenge lies in the realm of light, not law. Digital repatriation projects are creating a new kind of commons. By producing ultra-high-resolution scans of manuscripts and three-dimensional models of instruments, institutions can share perfect digital twins with museums and universities in the countries where these works were created. A student in Shiraz can now study, rotate, and virtually hold an astrolabe made by her city's ancestors centuries ago, even if the original brass remains in Paris. This is not about moving fragile artifacts, it is about moving access, ensuring that the cultural and educational benefit returns to the communities whose heritage it is. It acknowledges that while the physical object may have one home, its meaning and its story belong to a much wider human family. This ethical reflection is the final, necessary layer in honoring these engineers. To marvel at their celestial mathematics while ignoring the earthly journeys of their creations is to tell only half the story. True stewardship means making their legacy accessible in a spirit of shared human achievement, recognizing that the night sky they mapped belongs to no one nation, and the brilliance they harnessed is a heritage for all of us. Their gift was a map of the cosmos, but the way we choose to care for that map today is a mirror held up to our own values. Their story ends not with a telescope's first light, but with a quiet, enduring echo in our own minds. We have walked with those who measured infinity with brass and ink, and what we find is not a relic but a reflection. The true treasure of this celestial renaissance is the mindset it forged, a way of being in the world that feels urgently relevant. It was a mindset that saw no division between the beauty of a star and the geometry of its path, that believed a tool should be as lovely as it was precise. It understood that knowledge grows not from a single brilliant flash, but from the slow, steady accumulation of careful notes passed from one generation to the next. This reverence for patience, for collaboration across cultures and centuries, for building things to last, is their most precious inheritance. We navigate by satellites they could never conceive, yet we steer by a star chart they first drew with their naked eyes. We calculate with silicon, but we think within frameworks of measurement and proof they helped to establish. Their legacy is not locked in a museum case. It is encoded in the very way we ask questions about our universe. So the next time you glance upward at the night sky, pause for a moment. See more than the darkness and the distant points of light. See the grand collaborative project you are now a part of. See the patient observers who turned wonder into a map, and the master artisans who turned that map into a universe you could hold in your hand. Their journey reminds us that our greatest tools have always been human curiosity, disciplined attention, and the courage to build something beautiful, even when you know you may not live to see it finished. Let that inspiration guide your own observations, your own questions, and your own careful work. If this voyage through the mapped heavens has sparked something in you, we would love to hear your reflections in the comments below. And if you wish to journey deeper into the forgotten stories that built our world, consider subscribing to continue the exploration together.